30 gunshots. Deadly. No. Crap. They can do anything.
Hello and welcome to vlog number 81. The last one we covered basically the workshop I did on root cause failure analysis. A quick update on that, by the way. I had mentioned a project that was going on and some bias as part of the first part in relation to engineers. Well, it turns out the Iberian Peninsula report came out, or the Spanish blackout, and it was 180 degrees from what everybody was saying. As it turns out, the problems or what the cascading problem, because the original issue, what started the voltage variations, we can make some assumptions, but without actual data we can't say what it is. So we won't delve into that, which would defeat the purpose of what I'm about to say. That was, as it turns out, the alternative energy and storage helped the system hold on for as long as it did. It was actually the synchronous generators and the synchronous machines that fed into the problem per the study. So I thought that was particularly interesting. So in any case, this week we're going to get into practical electrical current signature analysis for electric machines. This was a course I just gave at EPRI. I had to adjust it a little bit because it appears that at a prior conference I had produced a paper and a presentation, and there was an employee of a competing company there, and a fair amount of my information showed up in this conference in their presentation, which was before mine, and the impression was given that their efforts, basically they were taking credit for my decades worth of work. I have never been so angry in my life. I consider that scummy, and just what a piece of crap those guys are. I've pulled out of a conference in which their person is associated with, and I'm waiting for a copy of that presentation to reach me so we can manage it through appropriate means. I do not like plagiarism, and I'm making that statement. It was absolute, complete plagiarism, right down to an error that I had placed in my presentation. So I addressed that in the presentation. It's so really, really, really bad when these investor-owned companies have to steal and lie in order to take care of their customers, who are the investors, not the users. So they had everything, including the history of the industry, mixed up because the person had taken really poor notes from my presentation. So that aside, let's get into this part here. I'm going to tell you the real history so that when they go out and they plagiarize this, and note, pay attention to who does it, and then remember this: if they have to plagiarize and they cannot answer the questions, how good is their equipment? Enjoy. So, practical and electrical current signature analysis for electric machines. My background, in which I've been involved in all of this for some time. I'm not some MBA who has decided he's an engineer in order to get money. But you know what? I'm going to stop now. Let's get into the actual history. So one of the things that had been brought up was that they were developing this method for determining insulation breakdown. Well, that's probably because I hadn't published the paper publicly at that point. This was 1 month ago. The paper I gave at IEEE because of the work that we've done for several years on this particular issue. This one here has to do with circulating currents. There's another company trying to take credit for that. I tell you, I've been just absolutely amazed. But in any case, that's why you're going to hear some of the true history of what's going on with these systems. So, electric machine system. Now, if I'm talking about electrical signature analysis involves taking data between the controls and the motor and taking voltage and current, and voltage data is upstream, current data is downstream from that into the process, et cetera, et cetera. So all of this involves being able to look at the entire system. Current signature analysis could be 1 or 3 phases or 2 phases, whatever is decided by the technology in order to look at the mechanical conditions downstream. What's particularly important, and I emphasize this because there were a lot of vibration folks at the EPRI conference, was that electrical signature and current signature analysis are literally vibration analysis. We just utilize the air gap of the machine as our transducer. This results in the fact that we do not get a lot of the resonances and other conditions that occur in the machine through the material of the machine, so that when we're looking for absolute numbers, not multiples of that number. So electrical signature analysis, the history, this, by the way, comes directly from Howard Haynes. It's not the whitewashed bit that was presented from my slide. But in any case, it comes from 1989, not 1995. And this was Howard Haynes' paper from Oak Ridge National Labs discussing a Venn diagram of what the different technologies are. The real history starts with Bill Thompson out of the University of Aberdeen in the late 1970s, getting into the early 1980s. He's the one who's attributed historically with identifying the pole pass frequency associated with rotor-related stuff. His primary focus was on rotor-related conditions, up to and including a book that he and Ian Culbert, who passed away in 2013, I want to say, called Current Signature Analysis for Condition Monitoring of Cage Induction Machines. That's this book here, published through Wiley, which is IEEE. Excellent book. I often reference it. My book is this one. That's Practical Electrical and Current Signature Analysis of Electrical Machinery and Systems. This I published in 2022. It is going to come out as a second edition through River Press next year with a lot more information. A lot of this stuff is already obsolete, but we'll get into that. Now, often incorrectly attributed is that Howard Haynes of Oak Ridge National Labs in the 1980s had focused on rotor testing. Had focused on rotor testing. He did not. His focus was on mechanical fault detection of motor-operated valves in the contaminated area of nuclear power, with a focus on bearing and gear faults. Now, I published. They first submitted for a patent in 1986. The actual work and papers, including work started at NAVC, started in 1985, or had been published in 1985 in a series of articles that go all the way up to 1995. The patent that did get submitted, and it's a misnomer here, it was later corrected, was Motor Current Signature Analysis Method for Diagnosing Motor-Operated Devices, in which the 1986 submission was withdrawn, and it instead was awarded in October of 1990. This is a sizable patent, and it goes through all of the things with a mention of rotors, but primarily all the stuff that I've been talking about, belts and bearings and everything else, early detection of these issues. And that was proven even through NAVC. And that gentleman's name was Chris Nemrich. So this also is from the 1989 paper. The concept that Howard Haynes has was that you would be able to go into a motor control center and look at the complete system instead of having to go machine to machine, and it would move much faster. And this is an accurate portrayal. So from his 1986 presentation, I have the full slide deck. He considered non-intrusive monitoring from the motor control center. It will look at aging and diagnostic information comparable to conventional instrumentation accelerometers, but without the attendant disadvantages, such as being able to locate the accelerometers, which is going to be something we cover in a series of papers, etc., because of several disasters we've been involved in investigating, but that's another story. Measurements can be performed rapidly by relatively unskilled personnel using portable, inexpensive equipment. Being able to collect data is a lot easier. You do want to have somebody who is familiar with electrical systems, because they're going to, if they have to open a cabinet and so on. It is very sensitive. Even then, when they were using strip tape and recorders, selected to a variety of mechanical disorders affecting operational readiness. So in effect, his focus was on the complete system, in particular the driven equipment. Also from the same slide deck, we have this. This was his drawing of the setup and all of the work that needed to be done. Remember, this is work done in the 1980s. And in this case, the whole idea was to use the motor to evaluate the pump in a system. This was published as part of a NAVC study. I have the papers over here. Chris Nemrich of NAVC has given me those in order to continue our work and our research. The sensor is this machine in particular. The sensor is this gap right here. Now, there are standards. There is a standard such as ISO 2958. There are other standards that have been in development. We did not get it into IEEE 62.2 quick enough, so it will not be in this iteration. We're introducing the next one, and that's part of the reason we've been doing a lot of the papers. I'm also the convener for the international project on ESA and MCSA through CGRE. So this one is a condition monitoring, diagnostics and machine systems, electrical signature analysis of three-phase induction machines. That's that standard. Now we do use this on transformers, DC machines, machine tools, any type of machine that has an air gap and a magnetic field. And again, also from Howard Haynes, he provided this so I could use it. It's the animation showing that as you move along, these motors see what's going on with the process. So each step of the process, it has an effect on current. This is the CGRE project, working group A178. It was approved in June of this year, and the first meeting is in August of this year. Now, this is one of the things that identified that situation I was talking about. Nice even air gap. If I have a nice smooth sinusoidal voltage coming in, I'll have a smooth sinusoidal current coming back out. If anything occurs to interrupt this gap, that could be arcing and sparking, partial discharge, wedges, rotor-related stuff, any torsional related, and that's the paper I'm giving at the end of the month at the Power Engineering Society meeting in Austin, Texas, is the relationship of torsional versus radial movement. Everybody assumed it was all radial, but it's not. It turns out that radial and torsional impacts on the air gap result in the same impact on decibels, which is why we can see driven equipment bearings, including the bearings of the motor itself, because we're not picking up radial movement, we're picking up the machine having to drive through that defect. Static eccentricity is with the rotor being pulled off center in vibration. That was termed unbalanced magnetic pull. Dynamic eccentricity is the orbit of the rotor inside the air gap. Now, the static eccentricity results in the number of rotor bars times the RPM plus and minus 1, 3, and 5 times line frequency. Now, this is the error I had introduced into the paper, into the prior thing, and I'd always meant, I forgot to change this slide when I do my presentation, but it's a deliberate error to catch exactly what happened. So it was not supposed to be line frequency, twice line frequency, and 3 times line frequency. It is 1, 3, and 5. That was very interesting, but neither here nor there. Other effects on the shaft include unbalance, that would be radial, torsional, which is torsional related stuff on the air gap, unbalance and misalignment, overtension belt, stuff like that, that's seen there. And smeared laminations will cause the rotor to bow and cause things like dynamic eccentricity. So we're going to circle back to this machine. Actually, we're going to do this machine next. I've got a case study. If you've seen my presentations, you know I've done this one a couple of times. Well, there's a lot of reasons for it. I've got great data on this. It's on a variable frequency drive. Yes, we have experience with variable frequency drives. As a matter of fact, whether you're talking about empath, Empower, PDMA, Baker, the traditional companies, and Alltest, of course, which is the empath. But in any case, being able to do work through inverter-driven equipment has been around since the 1990s. This is not something new. It was being incorrectly produced at EPRI as something brand new that required research. Sorry, as a matter of fact, the case studies I had submitted in my paper for EPRI were all inverter-based systems. So this is a 600 horsepower, 460 volt machine, as you can see here. This is the 6322 bearings that are on both ends of this machine. There's also some pump bearings in there. Didn't have them because we're not focused on that for this case study. The other thing is because the empath is a direct descendant of the Oak Ridge National Labs project, there's a definite torsional-based readout for it. As a part of what they were looking at was motor-operated valve torque. So this is one of our torque readings. We also calculate out not just the air gap torque, and it's different than taking direct shaft torque. That we brought up during another presentation at the conference by somebody else that was doing torque, and somebody said, well, ESA, and I said, well, they're actually different readings. One is air gap torque. It's a calculated value of what's going on in the air gap of the machine, and the other is a direct measurement showing the twisting of the shaft. It's a material-related torque. So they're different, and they both provide solid information for different types of things. In any case, one of the nice things, though, in that air gap torque, that allows us to take from the kilowatt data and determine what the actual output is, and the difference between these, that's my losses in the machine. Now, we've seen a couple of companies running around again, marketing bullshit and hype. I've decided that we're going with Squatch marketing now. I'm after this week and the feeling that people have no problem stealing other people's life's work, and I will no longer support people that adopt those technologies because they're going to be stuck having to deal with those folks and the bullshit that they get back which is they tend to blame the customer because they don't know what they're talking about. Not the customer, the manufacturers. So in any case, we get down to it. You can only have losses in the motor bearing between these values. And I had one of these companies, was not very precise, try to tell me once that a three-quarter horsepower motor, well, let's just even round it up to a 1 horsepower motor, but it wasn't, somehow produced 20,000 kilowatt hours in a year of losses from a slight problem with lubrication in a bearing. Well, let's see. 8,760 hours in a year, 746 watts in 1 horsepower. That means, or 3/4 of a kilowatt. That means that the maximum I can produce before the motor stalls is under 12,000 megawatt hours in a year. So there is no physical way in hell you can get 20,000 hours. The person then tried to quote that I was the one who came up with it for them, which was absolute bullshit as well. He didn't know who the hell I was, even though he claimed to be a good friend of mine. Neither here nor there. If you ever hear crap like that, oh yeah, we got it from Howard, reach out to me and let me know and ask me if I actually had anything to do with anything that sounds too good to be true. So in any case, getting back to the data analysis on this machine, bearings and more bearing related stuff here. So these are the bearing readings, basically. Here you can see these are peaks. You never, ever use DMOD to troubleshoot anything. I don't know why people are doing that. What can I relate this to? Absolutely nothing. You relate stuff to the peak, which is 0 dB down to the next level. If you have a peak here, what you're going to get is a lot of false positives because it's relative to the current. Linear analysis doesn't work for what we're trying to do in condition-based maintenance. So if you understand what you're doing, you do it in decibels. As a matter of fact, for continuous monitoring, we've tested it already ourselves. I'm not going to say maybe somebody came up with something that defies the laws of physics. But in reality, if you want to get fewer false positives, you want to get a highly accurate system, and that's what we've developed. You do your machine learning. AI. There's no freaking AGI. There's no ASI, and there's certainly as hell no AI. It's all machine learning. LLM, the original papers, go research it yourself. It's a simple view, is actually the papers related to machine learning for the LLMs. But marketing and hype, right? So in any case, count down to the level. That tells you the condition. Okay, these are all above 65 dB down, but I have a high noise floor, so I'm looking at above the noise floor. It's still 10 dB above the noise floor, meaning I have an issue. So when I come over here and I take a look, I can convert all of this over to watts or kilowatts. So 250 watts for a cage, that's because it's a larger bearing. You normally won't see anything more than a kilowatt in a standard bearing unless it's under a lot of stress. What we're actually reading is the friction losses. So the bearing, the cage, the ball and the outer race, these each will add up. Now 6322 is a gigantic bearing. And then the pump blade, which turned out to be a nick in the blade, caused a bit of trouble here. So up to 1.3 kilowatts in your larger machine. But you notice that this is well under the 10 kilowatts losses in the machine. There is some additional impeller blade problems, which we see here, which is about almost 3 kilowatts. That's a driven equipment related stuff. So between the bearings and this, I end up with a total of 5.5 kilowatts of the actual load, which was, I believe, let's go back to that. The actual load at the leads going into the motor is 126 or 127 kilowatts effectively. So this blade and bearing comes out to be 5.49 divided by 128, about 4.3% of the total load. So that comes out to be $5,500 per year, roughly, in additional cost to provide the energy necessary to feed these defects. Well, that, of course, I can calculate out. If I'm assuming 24/7 operation of the motor, makes the numbers look bigger. 5 times 5.49 kilowatts divided by 1,000 kilowatt hours per megawatt. So if I convert this over to megawatt hours, basically, multiplied to the present value of 0.699 metric tons. Metric ton is 2,240 pounds. CO2, because CO2 is heavier, per megawatt hour, and all the hype, but most companies have some type of carbon goal, and some actually have to deal with carbon credits. That is a reduction. Now, this is a different number than if I'm doing an inventory. You always use this value, because this is the avert value, to do it. So that is a potential reduction of almost 34 metric tons of CO2 by correcting the problems. It won't come out to that, probably be closer to between 28 and 30 tons. There's always going to be some level of friction. A couple of formulas to remember are here. To get hertz, because I like to do mine in hertz, it's RPM divided by 60. Synchronous speed is 120 times the applied frequency. Now this, if you're on an inverter, the output frequency of the inverter, but across the line, that would be 7,200 at a 60 hertz environment divided by the number of poles. So if a 2-pole motor, it's 3,600, 4 poles, 16 or 1,800, and so on. Slip is the slip minus the synchronous speed minus the running speed divided by the synchronous speed times 60. That gives me that. And in order to figure out my pole pass frequency, if I go twice that, then that gives me that pole pass frequency. This value here is the one we tend to use this for both current and voltage and ESA. But in order to get the decibels, it's 20 log 10 of the current in question divided by the primary current at the line frequency, or the RMS current. Always keep it. If you're doing peak, use peak. If you're doing RMS, you do RMS. Stator faults are the running speed times a stator slot. You won't see that peak. You will see the line frequency sideband. Static eccentricity, as we talked about before. Running speed times rotor bars. Line frequency 3 times, often 5 times. Now, depending on the type of filtering you're using and everything else, just like vibration, but with this, sometimes the sidebands will be higher or lower. Sometimes they'll disappear. I've seen a lot of other bullshit and hype out there because, again, certain people don't understand what the hell they're talking about. Depends on the filter or windowing you're using. You're going to end up with different size peaks. Don't always look to the right and don't always look to the left. What you're looking for is the highest peak in the countdown to that value. Always go after the highest peak. I've heard people say, oh, you always look at the left-hand peak. And bullshit. And then dynamic eccentricity is running speed sidebands around these. Now, if I don't have static eccentricity, I'll only see the calculated value for those running speed sidebands. If I have mixed eccentricity, which is both static and dynamic eccentricity, I will have both. The rotor bar sidebands now, depending on history, Howard Haynes had published this as well. It might be Bill Thompson, unsure, but mostly it gets attributed to Howard Haynes. But this is the values down from 0 dB to determine the severity of a rotor bar issue. By the way, whether I'm looking at a 0.5 horsepower motor or a 500,000 horsepower motor, it doesn't matter because everything's relative. This chart works with all of it. Now let's get into, for those who are into vibration, time waveform for us is kind of like this. So it'll be this or the RMS value. We'll take this is my peak to peak. So this is basically from 0 to almost 8 amps each direction. If I bring it down, it is 8 amps. This is the waveform itself, and you'll notice that I have noise on top and I have identical noise on the bottom. This, by the way, because here's my 0, is why we have sidebands instead of the exact value, because we see it on the upside and we see it on the downside. It's an amplitude modulated signal. I'm not going to throw the math in here for that, but know that it's plus or minus the carrier frequency, and this is my carrier frequency. Resolution is 1 over the number of seconds of data collected. This is the Empower unit. The Empower software we set up to do across 120 seconds. We chop off the first 10 because sometimes there's a settling time if somebody just clips on and takes data. So we chop off that first 10 seconds. So we go 110 seconds, 1 over 110 is 0.009 for our resolution or our bin size. Nyquist for ESA and MCSA is divided by 2. We don't have an aliasing issue until we get up past 48 kilohertz, so we're not too worried about that. So but we still do like 3 averages. That's common for ESA and MCSA. Why is resolution important? Because as the bin side is large, so this would be 30-second resolution, same machine, same set of data, real data, by the way. This is less than a horsepower machine. This one is a 100-plus horsepower machine. If I come down here and I take 30 seconds versus 60 seconds, or you can see that I've got a lot more information here. Now, the next step up, if I wanted to go to 0.001 hertz of resolution, I jump from 110 seconds to 15 minutes. So 2 minutes to 15 minutes. So in general, we found that that's more than enough, because we still need to separate out all of the bearings in the entire powertrain when we're taking a look at a system. Here's a good example. This is a motor with a rotor bar issue, casting void, so not something that'll be condemned, even though the value is a little on the high side. But they've got a lot of them because I've got harmonics of it. Okay, I'm running the motor in this case by itself, so I'm seeing those. But if I took just a 30-second data set, those pole pass frequencies, these are identical, it's the exact same set of data. We just chopped it down to 30 seconds. You can see the pole pass frequency hides in here. This would be my rotor bar related stuff. When I start looking at a larger spectra, now I limit it. This is off of the Empower system, which is 44.1 kilohertz sampling rate. My Nyquist is half of that, so technically it's 22 kilohertz. But we chop for purposes of maintaining your eyesight down to 5 kilohertz, which covers most things, including identifying the firing frequency of a VFD, which is right here. That's about 3,800 hertz, and then allows us to zoom in on other conditions. If I zoom in, I can see that I have some stuff going on. This is a synchronous belted machine. I know it's 4-pole, so 1800 RPM, which would be about 30 hertz. So, and this is exactly 60. So my running speed is going to be somewhere up here. I probably have a pole pass frequency in here, and these are belt-related issues. So it's a 60 horsepower machine or 45 kilowatts with 2 different types of bearings, 40 rotor bars, 48 stator slots. We provide, with decades of data, I have a lot of this information in our libraries. This is the Empower, and yes, we do defig wind turbines. Here's the same one with a little more data here. The rotor bar possible. Oh, by the way, the software auto detects the running speed down to 100th of an RPM. That was another thing the person who got up there just added to the whole thing while taking credit for everything they really didn't know what they were talking about because they could not figure out how you detect the running speed, and it's a really simple exercise. I'm not going to repeat it here. Look for it in my book. It's there. Rotor bars, unbalance or misalignment, and then bearing defects, and then I can come over here. We also developed an algorithm based upon historical data and a bunch of other stuff off of a single phase of current. We can estimate. So it's not as accurate as, say, the empath is with both voltage and current, which is extremely accurate, the actual watts losses. But that conversion allows us to identify small changes in watts, which would be indicators for things like lubrication well ahead of any other technology. 1 watt changes, even 10 watt changes will not be picked up with vibration or ultrasound. Probably why they don't have us on the P to F chart, because we're so far to the left they can't keep up. And it wouldn't help their marketing. But neither here nor there. I'm just going after everybody today. In any case, just kidding. I love all technologies. I use them all. But in any case, looking at the pole pass frequency, so this is the energy lost associated with the rotor bar, or the casting voids, casting voids in that case. Speed, belt was could be more significant, but total, we're only talking about 64 watts lost in that machine. When we start to, there's other things going on as well. And one of the reasons we had developed the Empower was to get out to this higher frequency. I noted that there's a company out there trying to say their oscilloscope is a MCSA device. It isn't. It doesn't have the capability to get the correct information. But that's neither here nor there. Everybody wants to copy the winner. 0 dB here, count down. This is part of the research project that we published recently. It's a multi-year project on detecting why fluting is still happening in bearings, even though, and then this is showing, this stuff here doesn't translate well to total harmonic distortion, which is one of the reasons we did this. This was an incidental discovery, by the way. We just pushed it out once we just said, wait a minute, the decibel concept is working, so we have relative harm and relative harm index based upon the relative energy present as presented in decibels. So that was the other paper we just published, as well as this one here, and it's a continuation. There's a continued study. This is a dynamometer machine. This one here is 2.5 megawatts, 690 volts. This is possibly a fractured rotor bar. So we take a look at this and see the pole pass frequencies there, which are relatively high, but it really didn't affect the operation of the dynamometer too much, so they had continued using it. Other things here have to do with the gearboxes that are on that. As we take a look at it, we're seeing the entire system. So these are bearings and gears, and then there's more frequencies further on. So the same one presented with the Empower system, except we use the Empower system. We actually now use them both together. So effective this upcoming week, we're going to be advertising that you can purchase an Empower and Empath combined system now for a discounted cost. So it's not a significant value more. It'll allow you to do these studies as well as have the full ESA capability. We're working on a translator for the data as well. We can translate data from the Empath to the Empower, but I haven't done the other way around. This is on the power side from the system, from the drive to the machine, and then this was measured on the surface of the machine on ground. And when we went ahead and we took a look at it, now some companies refer to this as stray current losses. We're measuring the air gap of the magnetic field stray fields from defect. Bullshit. They don't know what the hell they're talking about. I am sorry. An electric motor's frame, and we've proven this time and time again, is a Faraday cage. All you're measuring is the leakage. It also is a fantastic antenna, and I've already done several case studies where we had cranes overhead moving along. We were picking up the cranes, and we were picking up failing LED light bulbs off the surface of the machine when doing this. So if you have a predictive maintenance tool that's using flux, I call them the flux capacitors with pixie dust, and you're trying to trend off of that, everything around it that's emitting an electric field will be picked up. And so you might get a lot more false positives, which actually seems to be the case. False positives are phenomenally great because they drive your maintenance costs through the roof because you're running around chasing non-problems. So in any case, what we came up with from all that was a relative harm index. And that was produced, and how we came up with this was in the paper. This is the decibel level and in current, and this is the frequency level. So if I'm at 4 kilohertz, which is right around here, at 20 dB down, that means I'm at roughly at 2. So that comes out to be 10 to the second times more harmful than if I was in straight 60 hertz. So we said is anything that's 1 or more must be addressed sooner rather than later. So, 0 or more must be addressed sooner or later. So you'll see here as we approach 0, we go towards yellowish. I know I used blue instead of green, but and then as we get up here, it's red. At line frequency, that's our reference point to 0, so it's obviously 0. Now, why is this important? Well, that's because counter to what a lot of people put out there, again, hype from the 1990s, is a brush does not remove all current flow from the shaft. It's still split. So a portion of it goes through the bearing still, and a portion of it goes through the brush. And the idea is to drive the amount of current down, because the amount of current passing through the bearing has the effect, not voltage, current. Okay, everybody keeps poo-pooing current, but it's current that does the damage. Voltage just provides the potential. I can have a very low voltage and a high current. Now, traditionally, and I don't know why, but traditionally everybody says, oh, you have to take the voltage off the shaft, or you have to do all this stuff with the shaft. So you have to put yourself in extremely dangerous situations in order to gather data, when all you have to do is take a current clamp reading on ground. If you want, you can take a current clamp reading off the brush to see how much of the current is passing through the brush and how much is going to ground, and that'll give you the severity. In the meantime, the higher frequency means as I approach the higher frequency, my bearing becomes, here's the formula, my bearing becomes less resistive to current flow, it's the impedance, and my brush becomes a greater impedance or is more resistant to current flow. And so as we increase the frequency, we start to have problems. The other thing is when we start seeing these higher frequencies, we will start seeing winding stress. And the winding stress signature we derived, originally it's always been presented as being the winding short measurement. Well, the same formula actually turns out to be any type of electrically related, like sparking, partial discharge, that causes a variation in the magnetic field. So if I have variable frequency drives and they're not set properly, they'll cause more PD in that gap, and as a direct result, I'll end up with a signature. We did that study at several locations with several large companies in order to determine it. We found that when I see this signature, when it pops up, what I have to do is just make adjustments to the drive and it all goes away. Now, some of these that I had used in the thing were also reproduced, and I used different symbols than everybody else. These come directly from my book and my papers. So when I saw a big bold version of this in the presentation, I thought that was interesting. So running speed peaks rotor here, stator here. This is the actual formula for it. Why not? All has to do with the unbalanced magnetic pull. And then, of course, the stator slot frequency here, if I have line frequency sidebands or high raised noise floor around either one, that's indicating an insulation breakdown. That was our other paper. This is one of several. There's 4 types of insulation breakdown we identified and how they're derived. So this one here is actually off the skin of the machine. This was the setup here using the Empower unit and all the sidebands and everything. This is the low frequency end. This is the Empower. This is the empath. And then we looked up the higher frequency end and identified that it also had insulation breakdown, which they confirmed with a surge tester at the repair shop when it went in. Here's a synchronous fan application. This one here, you can see that I have 3 peaks right here. One of the things when you have experience with current and voltage, electrical and current signature analysis, we know how to compensate for this. That was another thing. Obviously, the other organization had no freaking clue because you have to have a little bit of experience. So check rotor bar, I respect companies that do the research. I look for the research and I give credit where credit's due. I do not like plagiarists. Check rotor bars, unbalanced or misalignment, they're thieves. OD and DE, bearing defects and all that other stuff in here. But what we had to do in the algorithm is you eliminate the extra peaks. Now, because we had the extra peaks and the problem they had, they thought they were going to have to make major changes to their system. All it turned out to be was making a slight adjustment to the VFD, had to turn the gain down a little bit, and a couple other adjustments, problem went away. The loss associated with the application, now this is where we were detecting the problems. The belted application, because of the improper setting, was 5.6 kilowatts, and then the higher readings here in watts in the OR and IR, outer and inner race of the bearing versus the other part, indicate it's actually a damaged bearing. Therefore, this is going to have to be worked on, and the losses are to the tune of $7,200 a year and 50 tons of CO2 for that area. So let's do 2 quick wind application things, because this has to do with how the relative harm index came about. The organization that started the work on this was a wind company, and then followed by another wind company, followed some work we were doing with the NREL. We were hoping to get the study moving forward. Unfortunately, for some reason, reliability of the energy grid did not fit this new bill that went through and needed to be cut. So NREL didn't have the funding to continue moving forward with the study at this point in time. Total U.S. capacity in wind, 195,000 megawatts. That includes under construction 156,000 megawatts is presently online. The rest is under construction. There are 73,736 wind turbines that are in operation. That includes on and offshore, greater than 1.5 megawatts. The average life should be about 25 years. We're not quite seeing that. And back in 2012, so this is some time ago, we know the numbers are much higher now. Catastrophic failures, 10% of generators would see it. Gearboxes, 5%. Main bearings, about 30%. Main bearings, just to put that into perspective, you can look down here, the costs associated with each. These are the minimum costs, not the average, actually, is this. Now, what was interesting is all of these had to do with electrical discharge machining, and it was during a separate study that we noticed that we had high circulating currents up tower. That led into future work and investigation. So we've had data from multiple organizations, all started with the original the original wind company that suggested this. So we didn't discover anything. We discovered what the root cause was, and that is actually that the grounding protection when we're in the nacelle has literally nothing to do with grounding the nacelle. It has everything to do with lightning protection only. And when you consider the amount of current up there, now all of a sudden the small size of the ground leads makes more sense. So they do have personnel protection all the way up. That's a required standard as well. There's no standard calling for the nacelle to be grounded to earth. So this is an example from the first company of where current data was taken. So on the generator itself, this is voltage and current on a brush on the main bearing, and then this is the size of the ground lead for basically three double-aught. I'm sorry, is it 1-aught or aught cables going up? Each cable's about yay round. And there's 3 cables on this particular design per phase, so it can carry about 1,500 amps. That is not going to carry fault current from up tower. So that's strictly lightning protection. And then they ground all the way up the ladder so you don't get shocked as you go up to 240 to 350 feet. This is the voltage and current from this type of generator. It was an induction generator. So it puts out the data at whatever frequency, then it goes down tower, and this is the type that has the inverter between the generator and the grid. They make up less than 6% of all the turbines. This is the generator where I showed the current clamp on the generator. That is about peaking at about 30 amps. Now, when I do these studies, we go off the peak current. And this is at the ground for the main bearing, and that's at 148 amps. So we take a look at all of that, and we take a look at the frequencies involved. So the at about 5 kilohertz, we're at about 18 dB down, and at 20 kilohertz, we're at about 40 dB down. Believe it or not, those are equivalent. And at 10 kilohertz, something amazing happens. The brush, that's about where the brush becomes, well, when it switches, and I've got more current flowing through the bearing than I do through the brush. So we go back again to this. There's some leads going down from the top to the yaw deck. Yaw deck is the deck immediately below the nacelle that turns, and we apply this here. This is all studies we've done since 2021. As we look at this, this is the bearing impedance coming down by frequency, and then these are a standard carbon brush and a silver carbon brush. And as you can see, the amount of current flowing, if this was based on 100 amps measured on ground, the amount, I still have some current going through the, at 22 kilohertz, I still have some current flowing through the brushes at about 20 amps versus 80 amps going through the bearing, or just shy of 70 amps. But I'm still dealing with a severe problem in which I'm going to have degradation in this bearing relatively quick. Okay, final wind power case study. If you followed my stuff, you've seen this case study before. Just to show you the sensitivity of the equipment. These are main bearings on GEs. They're 6330M bearings. I just recovered the bearing. I'm going to show you in a minute, so I have it because I want to get some newer pictures. And it's another one where I caught somebody using my materials in their presentation, claiming it was them, and I'll tell you why that was funny in just a second. Because okay, so there's a few. I didn't talk about this before, but this last week really got under my skin. So I'm calling them out. If you want to use my materials, give me credit for it. That's all I ask. We work on this stuff. We do practical applications. Half of my profit goes into the research to do this type of stuff and present this stuff. To come along and steal it outright which I'm going to go after recovering some of my stuff from the plagiarists, because it just so happens some of the stuff that came out of a copywritten book, like a registered copywritten book. And what's great about registered copyrights is you get to collect. So in any case, we'll get here. I can't, oh man, I really did get under my skin, didn't it? So in any case, taking a look at this all has to do with things in the gearbox. I'm not going to tell you what that is because I don't want to see that showing up. But these are related to the bearings. And there's one in there that caught us off guard. So this was, they had just replaced a bearing up tower. They took before and after readings. The after readings showed that that there was a problem going on in the gearbox. So this is the main thrust bearing of about 8.6 kilowatts. The ball, outer race, and inner race were a little heightened. So they were a lot higher than we expected. The total losses were about 11 kilowatts. So we had the bearing taken down, and they shipped it up to us to take a look at it. And this is the additional loss, this false Bernelling. I didn't have the cage, and the cage I really wanted, but they had removed the cage as part of removing the bearing, and they sent us up the ball. Now, these pictures here made it into somebody else's presentation. The fun part is that's me. That's my face. And that's a t-shirt that I have. While I'm taking the picture of this particular thing. So the person denied it, and I said, that's funny because that is literally my face. Had them expand the picture, and it was literally my face on their slide. So this one here was the ball dragging and everything else. When they put up the new one, and the reason I like this study is we had the same wind conditions, same direction, everything else. They put the new one up, and then all of those values dropped way, way down. This is not the same peak. That peak is now here. This peak is actually related to something else. And, of course, those peaks are now gone. And with that, thank you for your time. I appreciate the patience as I just, like I said, got fed up. I lost sleep over that one. I was so bloody angry because they did not hold back on what they did. So in any case, that's it. And we will do 82 hopefully next week. I produced 2 this week because I missed one last week. The other one, if you're really interested in, is the RCFA. And that one is a lot of fun as well. So thank you very much, and have a great weekend.